Okay, welcome to another Ginger Mathematician video where I'm going to go through the IBHL Applications and Interpretations Paper 2 that was recently sent out by the IB as extra practice material for the high-level application students. Unfortunately, I didn't get to go through this in my normal classes, so I'm recording a walkthrough video instead. So YouTube, you can benefit from this as well as I go through the questions. Okay, before we get started, please like and please subscribe. It goes a long way for helping the channel, and maybe there is a demand for high-level applications content. If there is, I'm more than happy to do some more videos. Right, let's get started. So, we're given a diagram which represents living accommodation on a university campus with this being 300 meters and the height here being 200 meters. And this is essentially a Voronoi diagram question. So that means if I'm at C and I'm over here, for example, then the closest office will be at C. Likewise, if I'm here, then B will be the closest. This is what the diagram represents. And we're told the equation of the perpendicular bisector of AC is 5x minus 2y equals 615. Now AC, so it's going to be this line here that's represented, like so. So this is our 5x minus 2y equals 615. And we need to find the x-coordinate of the point where this line intersects the line y equals 200 and y equals 100. Nice warm-up question. So when y is equal to 200, we pop this into the equation given. So we get 5x minus 400 equals 615. We add 400 on both sides, so 5x is equal to 1015. And then we pop this into our calculator. Actually, before I carry on, there are two documents that you need to have ready. Okay, we're not going through IGCSE. Maybe, unfortunately for yourselves, you might find this a bit easier. What we've got here is my GDC, so this is the calculator I'm going to use. Okay, you may have a Casio, but I'm going to be using TI Inspire. And you should also have this document here as well. This is the formula sheet for the applications course. You need to have both to hand as we go through these questions. Right, so let's go back to our GDC. We've got 1015 divided by 5, so we're going to pop that into here. Divided by 5 is 203, so we go back and write in 203, so that's our first value, and then for part 2, when y is 100, we pop that in, so we get 5x 200, 15, 5x is equal to 815, x is equal to, and we pop it in, and if you do this on the calculator, you'll get 163 as your answer. So this will help us later on, so we'll come back to those points in a moment. But in fact, we could even write them in now. So this coordinate, which will be useful later on, is 163, 100. And this one here was the previous one, so that was 203, 200. Okay, so these two coordinates here and here. Right, the manager in Office C believes that he has more than 1/3 of the area of the campus to manage. Excuse me, and we need to find the area of the campus managed by Office C. So the way I would go about doing this is split this into two shapes. Let's get my blue pen out. So I think I would split this down here, like so. So essentially we need to find out the area of the rectangle. Let me see if I can pop this up here. So the area of the rectangle, area of this triangle that I've just now made, and then add those together. So the area of the rectangle, well, let's have a think here. The height is 200. And then we're going to times that by going across. So that's going to be 97. This is 203. The end is 300. So we're going to work out 200 times 97. That gives us 19,400. You can check this on your calculator. And then the triangle, well, we can just use half base times height because this is perpendicular. So the difference between these is 40. Yeah, 163 and 203, that's 40. So we get 40 times the height, which is 200. Let's go this times this, and then divided by 2. And if we work that out, that is equal to 4,000. 200 divided by 2 is 100. 100 times 40 is 4,000. And then we add those together, giving us the answer of 23,400. And again, we have to be careful with units. You don't want to lose a mark just for units. Notice we've got meters in the question, so it's going to be 23,400 meters squared, or square meters, for our answer. Okay, let's move on. Question C, hence or otherwise, find the areas managed by offices A and B. So let's go back to our diagram. I think I can probably convince you here that A and B are essentially the same shape. So they share this line, they share this line, this is the same line. So you're probably agreed that the area of A, actually let me write this on the next slide, down here. So area of A is equal to area of B. Now the way I work out the area of this, if I go back, we already know the area of C. We can work out the area of the entire shape and then take one away from the other. That will give us the areas of A and B combined, and then we can divide by 2. So let's go through this. So the area of the entire shape, or the campus, so area of campus, try and give it a context, is 200 times 300, so that's equal to 60,000. Okay, so the area of C, let's see what that was equal to. That was equal to 23,400. I'm going to write that in again. So to work out the area of, say, A and B together, I'm just trying to write out my working here. So 60,000 minus 23,400 together, that's going to equal 36,600. Good, so area of A, which is equal to area of B, that's going to be equal to that divided by 2. Probably being a bit overkill on the working here. If I've got time, I would do this in the exam. So the area of both of these, 18,300 meters squared. Okay, so that's C done. And D states a further assumption must be made in order to use area covered as a measure of whether or not the manager of office C is responsible for more students than the managers of office A and B. So let's look at the context of the question. This is a living accommodation. So what they've assumed here is that the density of students, or density of living accommodation, is uniform. So what I mean by uniform is they're equally distributed. Be interesting to see what the mark scheme says. I would say uniform, or right, equally distributed. I think both would be fine there. So that's part D. So yeah, there's an even spread essentially of students across the campus. And then a new office is to be built within the triangle formed by A, B, and C. Excuse me. At a point as far as possible from the other 3 offices. Find the distance of this office from it for each of the other offices. So let me draw this on the board. So if I draw this triangle that's made, let's just talk about what a Voronoi diagram actually represents here. So this vertex here, this is the vertex that's the same distance away from A, B, and C. And this is in fact the point that we're looking for. This is the point that is the furthest distance away from A, B, and C. So a little bit of interpretation of the question here. And what we need to find then is find the distance of that office from each of the other offices. Well, I think the easiest way of doing this, we already know that C is at 250. We're told that, oh, there goes my mouse. Let me fix that quickly. We're told that C is at 250 on the x direction. Let me just write in the coordinate because we were told this. So 250, 100. We know this is 163 and 100. So if we find the difference between the x coordinates, so essentially we're looking for this distance, we'll have the distance that we want. And remember, this green distance is the same as this distance, which is the same as this distance. So it fits for all three scenarios. So we're going to go back and just take one away from the other, which is nice. So the answer is going to be 250 minus 163. And that gives us 87 meters. And that's our answer. So I'm just going to put the mark scheme. Yep, so just finding some attempts to the distance. I think the straightforward one to do here is just going horizontally across. There's no need to do Pythagoras or anything a bit more complicated. Let's just show the mark scheme. So in this PowerPoint, or maybe I can share this actually in the description below. So you can see where the marks are given. So your M1, A1, A1. Just a quick explanation. So M1 is method mark, A1 is an accuracy mark. And I think we see on the next part, if I'm not mistaken, an R1 mark. Okay, not on this particular question. Yeah, here. So you've got an R1 mark. This is called a reasoning mark, okay, which IB do have quite often. Okay, great. And if you're liking the content that you're watching currently, then please do consider liking and subscribing and sharing with your friends as well. Okay, thank you. Okay, let's carry on. So, question 2. A theatre set designer is designing a piece of flat scenery in the shape of a hill. Scenery is formed by a curve between two vertical edges of unequal height. One edge is 2 meters high, the other 1 meter. And you're given this diagram below. And you're actually told the maximum point, which is kind of helpful for later questions, which is 2, 3.5. So this is going to be 2, 3.5. We're going to use this in part B in particular. And a set designer wishes to work out an approximate value for the area of the scenery, A square meters. Explain why A is strictly less than 21. Well, let me draw the enveloping rectangle around this. So if I was to draw an enveloping rectangle around this. Now I don't need to go all the way up to 4, because I know the maximum point, I can actually go all the way across and create myself a rectangle which contains the actual area that I'm looking for. And the area of this rectangle, so the area, I'm going to do it in green, why not, is equal to 6 times, and yeah, 6 across and then 3.5 upwards, because that's our maximum point. And if we work this out, we get 21. So therefore we know that because this is smaller, so the blue is smaller than the area of the rectangle. We'll do this as a picture. Therefore we then know that A must strictly be less than 21. Okay, it's a nice straightforward way to start off. We have to get rid of this part in a moment. By dividing the area between the curve and the x-axis into two trapezoids, or trapezia, of unequal width. This is really important. When I first looked at this question, that was the part I didn't look at correctly. Show that A is greater than 14.5, justifying the direction of the inequality. So this is quite a nice 4 marks to get here, as long as you read the question. Now notice, as soon as you see trapezoids, you think trapezium rule. Right, fantastic, I've got the formula, off I go. But then they said true trapezoids of unequal width. So you go, okay, that's a bit strange. But we've got this really crucial bit of information, which is the maximum point. So what I can do is I can actually create two trapezia of unequal width. So notice this one is going to have a width of 2. And then this one here that I'm creating, going all the way across, has actually got a width of 4. So these are both trapezia. They both have a width of 4, and once we work this out, notice this shape together is going to be less than our curve, which is going to justify why the area has to be greater than 14.5. You'll notice in the mark scheme a diagram is sufficient for the working here. Now let's actually work out the area of these trapezia. So quick revision, area of a trapezium is equal to half A plus B times H. So let's now work out the area of A. Let's label these A and B so you know what I'm doing. So area of A is equal to half. Okay, now A and B are these lengths here, the parallel lengths. So you've got 2 and 3.5. And then we're going to times that by the width, which is 2. I'll work that out in a moment on the GDC. And area of B, so now we're looking at this one here. Well, that's going to be a half. Open brackets, we've got 3.5 and 1. And then we're going to times it by 4 because this is 4 coming across. So I'm going to go over to my GDC. I mean, you don't need a GDC for this actually because these two things are going to cancel. I was going to go to there, but we can just work this out normally. So this is going to be 5.5. This one here is going to be 4.5. This cancels with 2 here. Again, feel free to use a calculator at this point. That's going to equal 9. So the total area is 14.5 meters squared. And because of this part, I would actually shade this in to show that you're missing this part. Therefore, A must be greater than 14.5. Now, when we do the very last part of this question, you'll see that we do get an actual answer between 14.5 and 21. So the kind of questions you get on paper 2, they want you to sort of explore the topic a little bit more in depth than say on the paper 1. Okay, they'll put a line through for the T there. Perfect. Okay, but now we want a more exact solution, which is perfectly fine. In order to obtain a more accurate measure of the area designed and size to model the curved area using a cubic. So we've got a general cubic here. A, B, C, D are real numbers, and h meters the height of the curved edge. So we're going to try and actually find this function. Now the first thing we need to do is write down the value of D. Well, notice D, like with a quadratic or a straight line, this is always going to represent the y-intercept, regardless of function. I was telling my year 10s this the other day. So let's find the y-intercept. Well, it crosses at 2. So there we are. That's our answer. D is equal to 2. And now we need to use differentiation to show that 12a plus 4b plus c is equal to 0. So we've got our function h of x. Let's write this out. So ax cubed. Now actually the number's going to make no difference when we differentiate this, but that's fine. Let me pop it in anyway, plus 2. So we're going to differentiate this. So remember when we differentiate, we bring the 3 to the back, and then we reduce the index by 1, and then we bring the 2 to the back, reduce the index by 1. If we differentiate this, the x disappears and we're left with c, and if we differentiate a number, that differentiates to 0. Okay, but this is not exactly this, so we need to think there's another bit of information. Back to our maximum point. We know that when we set the differential to 0, that gives us then the turning point. Now we already know what the x value of the turning point is. It's equal to 2. So essentially, what we know is when x is equal to 2, reading it from our diagram, the differential of that function is equal to 0. So we're going to substitute x in. So wherever we see an x, we're going to put a 2. Okay, and this is going to be equal to 0. And then we just work out everything here. So 2 squared is 4, 4 times 3 is 12. So we get 12a, 2 times 2 is 4, so we get 4b, plus c is equal to 0. And I love these kind of questions because then you can just confirm that you've got the answer here that we're looking for. So we've got our first linear equation. We're going to have 3 in total. There we are. That's part D. Right, part E is we need to determine 2 other linear equations in A, B, and C. So we need to use now our diagram to actually work out what we have. So let's take 2 points. Now we know this point because we're told this from the question. So we want to take points that we're definitely sure of. This is important. So this is 6, 1, and we do know our maximum point. So what we're going to do is to generate these extra equations, we want to use these coordinates. Let's start with the first one. So when x is equal to 2, h of 2 is equal to 3.5. This comes out of just taking this coordinate. So we're going to substitute that in. So we get 3.5 is equal to a times 2 cubed plus b times 2 squared plus 2c. And we already know what d is, so that's good. So that's plus 2. And let's just simplify this out. I'm going to need more room on my next slide. So we get 8a plus 4b plus 2c plus 2. And yeah, I want to get everything number-wise on the left-hand side. You'll see why later on. So I'm going to rewrite this slightly as this. I'm just taking 2 from both sides here to give me 1.5. So that's my next linear equation. Okay, and now we need to do the other point as well. So we need to put in 6 and 1. So when x is equal to 6, y is equal to 1. Double check that is my coordinates. Yep, 6 and 1. So we're going to substitute that in. So 1 is equal to a 6 cubed plus b 6 squared plus 6c plus 2d was 2, yeah. I'm just double checking everything as you go along, that's very important. So 6 cubes 216. Feel free to use your calculator for any of these calculations. 6c plus 2, and now if we rearrange this, 216a plus 36b plus 6c is equal to negative 1. I'm minusing 2 from both sides, and we've got our equations. I think that's all we need for this. So we've done this, this, and this. And now this seems kind of random, but hence find an expression for h of x. Somehow you've got to find this particular function. So I'm going to write down all these equations we worked out. So 8a plus 4b plus 2c is equal to 1.5. 12a plus 4b plus c is equal to 0. Essentially, we've got a system of simultaneous equations here, where we've got 3 unknowns and 3 equations. Now, you're encouraged on the applications course to use your GDC. So that's what we're going to do now. So I'm going to try and minimize this, so at least I can see what I'm doing. So I'm going to do a split screen here. I don't like usually doing this because it's quite small, but I do need these equations. So I can still read that, that's fine. Let me reduce this down slightly. There we are. So I'm going to pop this into my GDC. So watch carefully. We're going to go to menu. We're going to go to algebra. Now this will work in your press to test mode. Solve system of linear equations. We've got 3. And I'm going to change this to A, B, and C. So it follows directly what we have. And now we're just going to write the equations in. Not the most exciting task in the world. So 36b, 6c. Easier when I'm using the software, but you can use this as well. So 8a plus 4b. With these kind of questions on IB, they do like to try and combine topics. So we're now looking at using a linear system to work out what these values are. So plus c equal to 0. We press the big enter button and we generate our answers. So what I'm going to do, I'm going to take a screenshot of this and pop this into here. There we are. So just check the answers that we get. Yep, I am happy with that. Good, I've got some room here. So I'm now going to write the full answer. So remember we've got D as well, so don't forget D when we write down our full answer. So let me open this up again. So h of x is equal to, we're going to round to 3 significant figures. So 0.0365 x cubed. Notice I've done this in order. So this is my A, this is my B, This is my C. So we have 0.521 x squared plus 1.65 x, and don't forget the plus 2, that's important as well. Okie doke. I'm just checking we've got the correct answers exactly as they want it. Yep, all good. So that's our question F. Completed there. And now for the final question. So we've done F. Use the expression found in F to calculate the A value for A. So we want to find the area under the graph, so we're going to use integration between 0 and 6. These are our limits. So essentially what we want to work out, we'll put it in sort of kind of short form. We are looking for the integral between 0 and 6 of h of x dx. Okay, which essentially is what we're looking for is 6, 0, this function here. If I just star this, we're going to pop that in here with respect to dx. Now, you're not expected to do this analytically on the applications course. You can use your GDC. So this is what we're going to do. So let's keep that. Let's minimize that down. And so what we're going to do at this point, again, this will also work on your GDC. We're going to go to menu, we're going to go to calculus, we're going to numerical integral, we're just working out a value here. We're going to go from 0 to 6. Yeah, we're working in x, so let's just type this in. So 0.0365 x cubed minus 0.521 x squared plus 1.65x plus 2. Everything good. We're working with respect to x here, so using the variable x. We press the big enter button and we get 16.014. Okay, now this is different to the main answer you get. I'll show you this in a moment, but it says in the notes here that they will accept this answer from the 3 significant figure answer, the part G. So they'll accept this answer of 16.014. Notice, there's one thing I didn't particularly mention at the time, is they say use the expression found in F to calculate a value for A. So we're not always looking for a very, very specific value here. So it gives you a clue. You are allowed to take the rounded answer. And we are going to put in 16.014 meters squared. Before I show you the mark scheme, notice if we go right back to the beginning of the question, we worked out an estimate between 21 and 14.5. And notice the answer that we got lies between the range. So if you're getting something completely crazy, like 50 or 75, then you know you've gone wrong somewhere. So do use that as a check to make sure you've done that correctly. Quick look at the mark scheme, so you can look through where the marks are awarded, the reasoning marks, for example. There's some good notes in here as well, so this can be shown in the diagram. This is what I did, for example. And yeah, we just worked through the algebra here. So nice question, combining integration, differentiation, working with functions as well. I like that question. That's a nice question, solid question, 16 marks. Make sure you're getting most of those marks. Okay, and on to question 3. So Dana has collected some data regarding the height, h meters of waves against a pier, 50 randomly chosen times in a single day. So I'm underlining key information as we go along, and we're given some frequencies that she has observed, and we are going to do a chi-square test at the 5% significance level, identifying this as we go along, to see if the height of waves can be modelled by a normal distribution. And null hypothesis, H0, is data can be modelled by a normal distribution. Again, before we even start here, we need to think the 2 chi-square tests that we know. So this is going to be a goodness of fit, because we're going to test the frequency that we have here against the expected value. From the table, she calculates the mean to be 0.828 and the standard deviation to be 0.257 meters. Use the given value of Sn to find the value of Sn minus 1. So at this point, we're going to use the formula that is on the formula sheet. So let me just show you where that is. So if I open this up like so, you'll see that the formula is written here. The unbiased estimate of the population variance. So we are going to copy that formula across. So we get s squared n minus 1 equals n over n minus 1 s squared n. And we want to find just the standard deviation, not the variance. So we're going to adapt that formula slightly. So let's go back and just write down that formula. So we have it there. So s squared n minus 1 is equal to n minus 1 squared n. Now this time we want to square root everything because we're looking for the standard deviation. So Sn minus 1 is going to equal the square root of n over n minus 1 Sn. Now we just use the values that we have here. So we're looking for Sn minus 1. What n, remember, is the total number of observations, so that's 50. So we get the square root of 50 divided by 49 times what we're given, which is 0.257. And we pop all that into a calculator, and let's just do that now. Our calculator, control square root, fraction 50 over 49, multiplied by the number 0.257, and then we get 0.2596. Again, always round to three significant figures, so we get 0.260. So let me just pop that in, like so. So we get our Sn minus 1. Fantastic. Okay, and in part B, we're going to look at the expected values that she's calculated for each interval under the null hypothesis, and the values are shown in the table below. So we're assuming that this follows a normal distribution and that it's distributed according to the probabilities of where it is within the range. So what we're going to do is use norm CDF to work out A and B. Okay, that will give us the probability of being within that range, and then we're going to times by 50 to give us the expected frequency there. So we are going to use norm CDF. Our upper and lower bound, let's do the first one together, and then I'll give you the answer for part B, but we do it in exactly the same way. So our upper and lower bounds will be 0.7 and 0.8. We're going to take the mean given in the question, 0.828, and then we're going to use the unbiased answer that we have there for the standard deviation, which is 0.260. So I'm going to go over to my calculator now, put this information in, and we're going to generate a probability. So we go to menu, we can go to statistics, we go to distributions, we go then to normal CDF, and then we write in our lower and upper bound. So for this one, it was 0.7 and 0.8. We then have our mean, which was 0.828, and our unbiased standard deviation of 0.260. We type that in, we generate our probability, and then once we have our probability, we're going to take that answer and times it by the total number of observations, which is 50. That will then give us the answer of 7.293. So I'm going to write down 7.29. That's the three significant figures. So A is equal to 7.29. And if you do a similar calculation for this one, so let me write down exactly what you put into your GDC. So this time we'll have 0.8 and 0.9. Again, same mean, same standard deviation. And if you pop that in, you should then get the answer of 7.6, like so. Okay, so you do it in exactly the same way as I did A, and you should get the answer of 7.6. So you get 7.29. And then 7.6. Great. Okay, and next part is find the value of the chi-square statistic, chi-square calculation for this test. And we're kind of going to work out the degrees of freedom as we go along as well. So I've done a bit of research into this on the high level course, and what we need to realize, even though it's not given in the question, is that we actually notice this 0 to 0.5, because this is not a range of 0.1 like these, that's from 0.5, this is actually quite a small frequency. Okay, if we think about in terms of the range it's going between, and it's the same at this end as well. So in order to make the chi-square statistic more reliable, this is what my research has come to here, then we need to actually merge these two columns together, and likewise these together. Okay, so they want you to realize, don't really prompt you with this, to actually merge these together. And that gives you a more reliable chi-square statistic. So we're going to write a new table on part C. So I'm going to draw a nice table, nice and clear, so we can see what's going on. And this time we're not going to need 1, 2, 3, 4, 5, 6, 7, 8, 9 columns, but we're going to need 7 instead. So the first one is going to be represented, so 1, 2, 3, 4, 5, 6, 7. So this one's going to be h is less than or equal to 0.6. So that's going to represent these two actually together. Okay, so then let me draw the rest of the table. Right, so this is going to be the frequency, and this is going to be the expected frequency. Okay, so the frequency will be 5 plus 2, which is equal to 7. So I'm going to put 7 in here, and that's the observed frequency, sorry. And the expected is going to be these two added together. So 5.2 plus 4.3 gives you 9.5. This is going to have an effect on our degrees of freedom, which I'll talk about in a moment. So then we go 0.6 to 0.7, 0.7 to 0.8, and so on. And then at the other end, we're going to then get h is greater than 1.2, which is going to include those two together. Greater than 1.1, sorry, which is going to basically include these two together. So h is going to be greater than or equal to 1.1. So again, we're doing this kind of merging idea. So in this one here, we get 6, like so. And our frequency together is going to be 7.4. And then for these ones, well, we already have them all set up, so we're just going to copy these across. So we get 4, 9, 10, 7, 7, 4, 9, 10, 7, 7, and then we can just read off the values that we did before. So we get 6.1. Just checking we've got everything correct here. So 6.1. Yeah, and we just copy these across to 7.29, 7.6, and what are the last two? 6.8 and 5.3. So we've got everything there. Okay, this will give you a more reliable chi-squared statistic. Okay, so at this point now we're going to pop this into our GDC, and then we're going to work out our chi-squared statistic. Okay, so in order to do this, I've also labeled my columns here. This is my expected frequency, and this is actually the frequency observed. Okay, we could put O for observed. I think that'll make our life easier a bit later on. We go to menu, we go to statistics, we go to stat tests, we go to goodness of fit, so chi-square goodness of fit. Our observed list, I'm going to call that O. Our expected list, I'm going to call E. Now our degrees of freedom, we're going to answer this in a later question. So normally it's one less than the number of columns that you've got, but we've also reduced down the parameters. So actually you're taking away 2 of those extra columns. So we're actually going to do 7 minus 3, not 7 minus 1, which gives us 4. Again, I'll answer that in part D in a moment. We press OK, and then we spit out our value of chi-squared, which is 3.35. So let's go back to this. Our chi-squared value is 3.35. Now I'll just explain the degrees of freedom again. Now normally it'd be 1 minus the row, 1 minus the column, which gives us 7 times 1, which is 7. So I've got that right. Yeah, so 7 normally, we minus 1 because of the row, and then we minus an extra 2 because I removed this one here and this one here merged it, so actually our degrees of freedom will be equal to 4. You kind of needed that to work out the chi-square statistic and working that way round. So now we've got C and D correct. Now we need to look at E. So now given the critical value is 9.49. Now notice we've got 3.35 here. You could use the p-value to do this, but notice that 3.35 is less than our critical value, 9.49, and therefore this means that we accept H0. This works in the opposite way to the p-value. Okay, and then you usually have to write a sentence here. So you can then say that the height of the waves are normally distributed. Remember that was our initial H0, like here. So H0 is the data we model by a normal distribution. Because we've accepted H0, I'm just writing a context sentence, which is the height waves are normally distributed like so. Okay. Just one thing to show you before I finish as well. So if we did it by using the p-value instead, we have to be very careful. Notice the p-value is 0.5009. Our significance level, this is an alternative way of doing this question, is 0.05. And because 0.50 is far bigger than 0.05, we can also conclude we accept H0 as well. So keep that in mind. The mark scheme is here. Hopefully I've explained well to you exactly why we've actually merged these together, because of the range. It's quite sneaky, this question, because of this range being so wide. This is why we had to merge them into one to make our chi-squared statistic more reliable. And the rest of the mark scheme here. So this explains why this is 4. And then we did this using the mark scheme way by looking at the chi-squared statistic, but you could look at the p-values to actually work this out as well.